Have you ever wondered how computer-generated imagery in films, video games, and architectural visualizations are brought to life? The answer lies in a fascinating process called 3D rendering. In essence, rendering is the digital art of transforming 3D models into 2D images that mimic real-world visuals. Imagine creating a stunning cityscape within a 3D modeling software. You meticulously place buildings, cars, and even tiny pedestrians. However, until you hit that render button, your creation remains a mathematical representation hidden within the digital realm. Rendering breathes life into these virtual worlds, simulating the way light interacts with materials, textures, and shapes. This transformation is not merely about creating a visual replica, it's about evoking emotions, telling stories, and pushing the boundaries of creativity. A well-rendered image can transport you to fantastical realms, showcase innovative architectural designs, or simply capture the essence of everyday life with breathtaking realism. As you delve deeper into the world of 3D rendering, you'll uncover a realm where artistic vision meets technical expertise. It's a journey of continuous learning and experimentation where mastering the art of rendering unlocks a universe of creative possibilities. The journey from a 3D model to a photorealistic image involves a complex series of computations known as the rendering pipeline. This pipeline can be visualized as a well-orchestrated assembly line where each stage contributes to the final masterpiece. The process begins with a 3D scene meticulously crafted by artists. This digital stage encompasses everything from the arrangement of objects and characters to the definition of materials and lighting. Once the scene is set, the rendering pipeline swings into action. The first stage involves transforming the 3D objects into a 2D perspective, much like a virtual camera capturing the scene. This involves complex mathematical calculations to determine which parts of the objects are visible and how they appear from the chosen viewpoint. Next, the renderer simulates the behavior of light within the scene. This stage, known as shading, determines how light interacts with different materials. Does the surface appear shiny or matte? Is it transparent or opaque? These calculations are crucial in creating realistic surfaces. Finally, the renderer adds the final touches, simulating effects like shadows, reflections, and depth of field. These elements contribute to the overall realism and visual appeal of the rendered image. Understanding the rendering pipeline is crucial for artists and designers as it provides insights into how different parameters affect the final output. By mastering this pipeline, you gain greater control over the rendering process, allowing you to create stunning visuals that align perfectly with your artistic vision. In the world of 3D rendering, various techniques offer distinct approaches to simulating the behavior of light and creating realistic images. Two prominent techniques that have revolutionized the industry are rasterization and ray tracing. Rasterization, the more traditional approach, operates by dividing the 3D scene into a grid of pixels. For each pixel, the renderer determines which object is visible and then calculates the color of that pixel based on the object's material and lighting. Rasterization is known for its speed and efficiency, making it suitable for real-time applications like video games. Ray tracing, on the other hand, takes a more physically accurate approach. It simulates the path of individual rays of light as they travel from the light source to the viewer's eye. By tracing these rays, the renderer can accurately calculate reflections, refractions, and shadows, resulting in incredibly realistic images. Global illumination, a powerful technique often used in conjunction with ray tracing, further enhances realism by considering both direct and indirect light sources. Imagine sunlight bouncing off a brightly colored wall, indirectly illuminating nearby objects. Global illumination captures these subtle interactions, creating a more natural and immersive environment. The choice of rendering technique depends on factors like desired realism, computational resources, and project requirements. While rasterization excels in speed, ray tracing reigns supreme in realism. Understanding the strengths and limitations of each technique empowers artists to make informed decisions that align with their creative goals. In the realm of 3D rendering, render engines serve as the powerhouse, the digital artist's secret weapon for transforming imaginative 3D models into breathtaking visuals. These sophisticated software algorithms are the driving force behind the rendering process, dictating how light interacts with objects, materials, and textures in a virtual scene. Think of a render engine as a virtual photographer, equipped with an array of lenses, filters, and lighting equipment. Just as a photographer meticulously adjusts settings to capture the perfect shot, artists rely on render engines to fine-tune parameters and achieve their desired aesthetic. From simulating the intricate interplay of light and shadow to replicating the subtle nuances of different materials, render engines play a pivotal role in shaping the final look and feel of a rendered image. Whether you're aiming for photorealism, stylized visuals, or anything in between, choosing the right render engine is paramount. Each engine comes with its own set of strengths, weaknesses, and specializations, making it crucial to select one that aligns with your artistic vision and project requirements. Section 5: Types of render engines: CPU, GPU, and hybrid. The world of 3D rendering offers a diverse array of render engines, each harnessing the power of different hardware components to bring virtual scenes to life. Among these, CPU-based, GPU-based, and hybrid render engines stand out as the most prevalent, each with its own set of advantages and limitations. CPU rendering, as the name suggests, relies on the processing power of the computer's central processing unit, or CPU. CPUs excel at handling complex calculations sequentially, making them well-suited for scenes with intricate geometry or simulations. However, CPUs typically have fewer cores compared to GPUs, potentially leading to longer render times for scenes with high polygon counts or complex lighting. GPU rendering, on the other hand, leverages the parallel processing capabilities of graphics processing units, or GPUs. Originally designed for handling real-time graphics in video games, GPUs possess a massive number of cores, allowing them to process vast amounts of data simultaneously. This makes GPU rendering significantly faster for scenes with complex textures, high resolutions, and effects like ray tracing. Hybrid rendering, as the name implies, combines the strengths of both CPU and GPU rendering. These engines intelligently distribute rendering tasks between the CPU and GPU, optimizing performance based on the specific requirements of the scene. Hybrid rendering offers a balanced approach, leveraging the strengths of both hardware components to achieve faster render times and handle complex scenes efficiently. The choice between CPU, GPU, and hybrid rendering depends on factors like budget, desired render speed, and scene complexity. Artists often experiment with different engines to determine the optimal solution for their specific needs, striking a balance between performance, quality, and creative control. Section 6: Popular render engines, industry standards. The world of 3D rendering boasts a diverse ecosystem of render engines, each with its own strengths and areas of expertise. Among these, Blender Cycles, V-Ray, Arnold, and RenderMan have emerged as industry standards, renowned for their exceptional capabilities and widespread adoption. Blender Cycles, the native render engine of the popular open-source 3D software Blender, has gained immense popularity for its ease of use, versatility, and impressive results. Cycles is a physically based, unbiased render engine, renowned for its realistic lighting and ability to handle complex materials. Its seamless integration with Blender makes it an ideal choice for both beginners and experienced artists. V-Ray, developed by Chaos Group, is a versatile rendering engine known for its exceptional speed, photorealism, and extensive feature set. Widely used in architectural visualization, product design, and film, V-Ray excels in creating stunning imagery with lifelike lighting, accurate reflections, and realistic materials. Arnold, another prominent player in the industry, is a Monte Carlo ray tracing renderer, renowned for its ability to handle complex scenes with ease. Developed by Solid Angle and later acquired by Autodesk, Arnold is a favorite among VFX studios and animation houses, thanks to its speed, efficiency, and ability to produce high-quality visuals. RenderMan, a veteran in the rendering world, has been a cornerstone of the animation and visual effects industry for decades. Developed by Pixar Animation Studios, RenderMan is renowned for its exceptional image quality, advanced features, and role in creating iconic animated films. Its physically based rendering capabilities and robust tools make it a top choice for demanding productions. These industry-standard render engines represent a small fraction of the vast array of options available to 3D artists. Each engine brings its own unique strengths and specializations, catering to different workflows, budgets, and creative visions. Section 7. Key features of render engines. Modern render engines come equipped with an arsenal of powerful features, empowering artists to create stunningly realistic and visually captivating imagery. Understanding these key features is crucial for harnessing the full potential of these sophisticated tools. Global illumination, or GI, stands as a cornerstone of realistic rendering, simulating the intricate interplay of direct and indirect light within a scene. Unlike traditional lighting methods that only account for direct light sources, GI considers how light bounces off surfaces, creating more natural and immersive environments. Physically based rendering, or PBR, has revolutionized the way materials are represented in 3D rendering. PBR materials are designed to accurately mimic the way light interacts with real-world surfaces, taking into account properties like roughness, reflectivity, and subsurface scattering. This results in materials that look and behave more realistically, enhancing the overall believability of the rendered image. Dynamic simulation breathes life into 3D scenes by simulating the movement of objects and materials based on real-world physics. From flowing fabrics and crashing waves to exploding particles and realistic hair, dynamic simulations add a level of dynamism and realism that would be impossible to achieve through manual animation alone. Multi-threading and distributed rendering are essential features for tackling complex rendering tasks efficiently. Multi-threading allows the render engine to distribute rendering calculations across multiple CPU cores, while distributed rendering takes it a step further by harnessing the power of multiple computers connected over a network. These techniques significantly reduce render times, especially for high-resolution images and animation sequences. By mastering these key features, artists can elevate their 3D renders to new heights of realism, creating immersive and visually stunning experiences that captivate the viewer. To Section 8. Optimizing your renders for efficiency. In the pursuit of creating stunning 3D renders, optimizing your workflow and scene setup is paramount for achieving efficient render times without compromising quality. By implementing a few key techniques, artists can streamline the rendering process and maximize their creative output. Optimizing scene geometry is crucial for maintaining a balance between visual fidelity and render performance. High-resolution models with millions of polygons can significantly increase render times. Techniques like retopology, which involves creating a lower polygon version of a high-resolution model and using LODs, or level of detail, which displays different levels of detail based on distance from the camera, can drastically reduce polygon count without sacrificing visual quality. Optimizing render settings is equally important. Adjusting parameters like ray tracing depth, shadow quality, and global illumination settings can significantly impact render times. Experimenting with these settings and finding a balance between quality and performance is crucial. Hardware plays a vital role in rendering performance. Investing in a powerful CPU with multiple cores, a high-end GPU with ample VRAM, and a fast SSD can significantly reduce render times. Additionally, ensuring adequate RAM and optimizing system settings for rendering can further enhance performance. By implementing these optimization techniques, artists can streamline their rendering workflow, reduce render times, and focus on what they do best, creating stunning 3D art. Section 9. Best practices for mastering 3D rendering. Mastering the art of 3D rendering is an ongoing journey of learning, experimentation, and refining one's skills. By embracing best practices and adopting a mindful approach, artists can elevate their craft and consistently produce exceptional results. Understanding the intricacies of your chosen render engine is paramount. Each engine has its own strengths, weaknesses, and optimal settings. Taking the time to delve into the documentation, explore tutorials, and experiment with different parameters will unlock the engine's full potential. Optimizing render settings is crucial for achieving a balance between quality and render times. Start with default settings and gradually adjust parameters like ray tracing depth, shadow resolution, and sampling rates until you achieve the desired level of visual fidelity without unnecessarily increasing render times. Leveraging shortcuts and techniques can significantly streamline your workflow. Mastering hotkeys, Utilizing render passes for greater control over compositing and exploring procedural techniques for generating complex textures can save valuable time and effort. Regularly testing your renders throughout the process is essential for identifying and addressing any issues early on. Don't wait until the final render to check for artifacts, lighting inconsistencies, or material errors. By incorporating regular testing into your workflow, you can ensure that the final output meets your expectations. Mastering 3D rendering is a rewarding endeavor that opens up a world of creative possibilities. By embracing best practices, continuously learning and refining your skills, you can push the boundaries of what's possible and bring your artistic vision to life with breathtaking realism.